Good day, ladies and gentlemen. My name is Rikhotso Vukosi from the University of Limpopo in South Africa. Today I will be presenting under the topic of the evaluation of two detection algorithms for distributed denial of service attack. This is my presentation outline, the introduction, the aim, objectives, methodology, results, and lastly will be my conclusion. So in the introduction, recently technological advances in ICT have resulted in the establishment of a cyber world in which the processes are done electronically with speed. So these advances are increasing the complexity and the information overload while reducing the decision-making durations. So the diagram that you see here, it's for the distributed denial of service attack. So this is the attack that we were working on the study. So basically, distributed denial of service attack, it's a cyber attack on a specific server or a network with intended purpose of disrupting the network or server's normal operation. So it basically floods the targeted network with a constant flood of traffic, such as fraudulent requests, which overwhelm the system, causing a disruption of or a denial of service to a legitimate or traffic. So mitigating this risk of distributed denial of service attack can help many organizations to be safe. So this is how a distributed denial of service attack. And then here we have the network that we're working on, the software-defined cognitive radio network. So this introduces a programmable, dynamic, adaptable, well-managed, and cost-effective network architecture. So software-defined and cognitive radio network, it's a recent improved networking architecture that separates the data plane and control plane in a network. So it is a networking paradigm that aims to solve issues like standard switch configuration and network administration. So in software-defined cognitive radio network, the controller is centralized and make it have a network overall view, which makes it outperform the conventional networking technologies in terms of cost effectiveness, agility, and programmability. So however, the security attacks such as distributed denial of service attack may overwhelm the network. So several attacks are vulnerable to the controller, such as a single point of failure. So which makes it which makes the servers inaccessible due to these attacks. So the software. So basically, the software-defined and cognitive radio network, as you can see, is the combination of the software-defined network and cognitive radio network. So it's just the combination of the two networks which formed this new recent network. So software-defined networking, it employs an open standard-based and vendor-neutral approach using the open flow protocol for realization of the software-defined cognitive radio network architecture. So the other one, which is cognitive radio network, is an adaptive, intelligent radio and network technology that can detect the available channels in a wireless spectrum and change its transmission parameters to adapt to the spectrum environment. So it can also enables a number of communication sessions to run concurrently, and then it's also an intelligent, reconfigurable, and dynamic radio technology. So the aim of the study is to evaluate the two detection algorithms for the distributed denial of service attack, which is the net plumber and the net plumber and the cloud-based algorithms. So the objectives of this study is first to evaluate the distributed denial of service attack detection algorithms, and then investigate the effects of the distributed denial of service attack in the software-defined cognitive radio network, and then evaluate the distributed denial of service attack security schemes, and lastly, evaluate the efficiency of the distributed denial of service attack detection schemes. So in the methodology of this study, we used MATLAB to carry out the simulations of the study, and then we also used the cluster sampling to sample the nodes in our network, where the nodes were ranging from 20 minimum to 150 as the maximum number of nodes that we can have. So in the population of our network, 150 nodes were the maximum number of nodes that we have. So it was divided into 4 clusters, and then we also had the different percentage of the attacking nodes, where it was ranging from 30 to 90% attacking nodes. So actually we had 30% attacking nodes, 60% attacking nodes, and 90% attacking nodes. So the 4 clusters that we divided, it was the 30%, it was 30, and then 50, 80, and 150 for each scenario with the attacking nodes. So as we continue with the methodology, the controller that we used for our study, it was the POX, and then the routing mechanism, we were considering the shortest path, and then the network topology was 3 array, and simulation area, the network, it was 300 meter by 400 meter. So the algorithms that we used in this study, it was the cloud-based and the NetPlumber detection algorithms. So another thing is the metrics that we used to evaluate the performance of these schemes. So we used the CPU. We also used the we also used the memory consumption, the bandwidth, and the number of packets. So this is just the first diagram of the results that we've got. This diagram was conducted in terms of the CPU and memory consumption with 0% attacking nodes. So as you can see from the graph, that during these experiments, we monitored the bandwidth usage and consumptions of the CPU, time of the controller, the response rate, and also the memory utilization of the controller. So the study also evaluates the usage of the resources on the controller under the normal condition where there is no attack. So this is where we got these results, where there is no attack. So to ensure that the results are not distorted, all the processes on the machine were disabled. So in order to effectively monitor the usage resources of the controller, then the bandwidth of the controller was set to 1000 Mbps, and then the memory controller was set to 1.7 gig, and the CPU was set to 1.8 gigahertz. And then the study also evaluated the response rate of the controller, where the CPU and the bandwidth results are shown in this graph and this following graph. So the attacking nodes generate a large amount of traffic that are forwarded to the controller, as you can see from the graph. So the streams of the generated traffic degrade the performance of the controller to extent that it may not even provide service to legitimate nodes. So we can see from this graph that when they were 100, and the number of nodes were 100, and then in the network, the traffic rate was observed to be 548.88 Mbps. So this is a large traffic that cannot be handled by one controller actually. So increasing the number of nodes is likely to degrade the controller's response time. So it also consumes a lot of CPU time, while few nodes require less CPU processing time, as you can see from this graph. It also consumes a lot of memory when the number of nodes is increased. We can see from this diagram as well. So when the number of nodes were set to 80, and 36% of the memory were utilized, while 100 nodes, it was 40% memory consumption. And then if the number of nodes were kept increasing, then the controller is likely to crash when 100% of the CPU time were utilized. So this may also cause some bottleneck in the connection. So these graphs, this first one and the second one, it was without the attack. we were monitoring the CPU utilization and memory consumption. And then on this graph, this is where we started comparing our algorithms, where is the NetPlumber and the cloud-based. You can see from the legends there that cloud-based is in blue in our bar graph and the NetPlumber is in red. So in this first figure here, we compared the performance of the cloud-based and NetPlumber detection algorithm to find out which of the two schemes detects earlier the DDoS attack. So the cloud-based algorithm detects the DDoS attack within the first 660 packets when the number of nodes is 20 in the network. So as we can see here that the cloud-based managed to detect the attack within the 650 packets. So the number of received packets decreased for all detection schemes as the number of nodes in the network increased, as shown in this figure. So you can see that as we increase the number of nodes in the specific network with 30% attacking nodes, and then the number of packets, they increased as they were detecting the attack. So this figure also shows the performance of the algorithms as the number of nodes were increased in the network. So this increased the amount of traffic in the network. So suppose that if a specific node can produce 100 packets in this scenario, maybe per millisecond, when the number of nodes in the network is 100, and then 40 malicious nodes in the network were gonna be consumed, and then also 700 packets per millisecond will be generated. So in this case, we can say that the NetPlumber detection scheme outperformed the cloud-based algorithm. So it also detects the distributed denial of service attack within the first 590 packets. As you can see here from this graph, when the number of nodes is 20, it's 590 packets. And then from this figure, we also compared the algorithms, but on this time we increased the attacking nodes, where the attacking nodes it's 60% attacking nodes. So the results in this figure here of 60% attacking nodes shows that the NetPlumber and the cloud-based schemes were still performing better compared to the scenario with 30% attacking nodes. They will be able to detect the attack within the least number of packets received compared to when the scenario was 30% attacking nodes. So, however, the NetPlumber detection scheme performed better than the cloud-based algorithm. So these experiments, we ran them 3 times to verify the results. So we observed that as the number of nodes in a network increased and then the detection rate improved, the NetPlumber detection algorithm managed to detect the attack within the first 435 received packets in a network with 100 nodes and 60 malicious nodes, which produced 2,000 streams of packets per milliseconds worth of traffic. So as you can see from this graph that when we have the number of nodes as 100, and then the NetPlumber and the cloud-based, where the NetPlumber performed better with 435 received packets. So this is the last scenario that we used of the attacking nodes, which was 90% attacking nodes. So then in this figure, it shows the results of this last scenario where we have 90% of the attacking nodes. So the NetPlumber detection algorithms was observed as the one performing better compared to the other scenarios. So you can see from this last node, which is 100 node, that this one performed better with packets of 410. So this is the best scenario that we managed to get from the system. So Lastly, it was comparing the memory consumption and the CPU usage for these two algorithms. So, as we can see that from the memory usage, after detecting the scheme that is also lightweight in terms of CPU and memory usage, the cloud-based at some point performed better than the net plumber detection algorithms, that as you can see from this graph. And then, however, it consumed a higher percentage of the CPU and memory of the controller as compared to the net plumber algorithm. So the net plumber consumed less memory and the CPU time. So therefore, it takes less and fewer packets to detect the attack as compared to the cloud-based algorithm. So this figure 6, this figure, it shows the memory utilization of the results. So the results presented in this figure, it showed that the net plumber detection algorithm is best performing scheme in terms of the CPU consumption. So it also consumed 26% of the memory, while the cloud-based it consumed 30% on average. So the cloud-based is also poor in terms of detecting the distributed denial of service attack. So lastly, the diagram of the CPU usage shows that it represents the CPU usage of the two detection algorithms. So the net plumber detection algorithm achieved the better performance as compared to the cloud-based algorithm. It consumed the least amount of CPU time. It also consumed 47% on average of the controller CPU time. And then the other algorithm, which is cloud-based algorithm, is also performing worse compared to the other scheme, which consumed 48.2% on average. So this way, just the comparison of the algorithms that we have in our study to determine which one performs better in the study. So the effect of the distributed denial of service attack on the controller, it shows that the flooding of the controller by distributed denial of service attack can directly affect the controller with a stream of packets. So these packets cannot have a match in the flow table where it was sent to the processor. So in conclusion, in this study, we investigated the two algorithms where we managed to find out that the net plumber performed better than the cloud-based algorithms. And then we also observed that the controller can withstand the attack for a few seconds when the number of malicious packets is less than 300 Mbps. So in future work, we can advise to try as many controllers as we can so that we can be able to detect these attacks at any point. I thank you.